A gray morning in Venice casts a veil over the canals as the MOSE barrier rises with breathtaking grace. 12 massive gates, each weighing more than 800 tons, break the surface of the lagoon. They are clad in thick steel, shimmering against the water as they prepare to face the invading tide. This moment, both tranquil and intense, captures the essence of engineering ingenuity, giant movable structures designed not to traverse the seas, but to hold back nature itself. Yet, a question emerges amidst the splendor of this scene: why are the world's largest movable structures not ships, but flood barriers? To many, it might seem an oddity that the titans of engineering reside not in the domains of maritime vessels, but in these sprawling flood defense systems. After all, a massive container ship like the Maersk Tripoli class can weigh over 200,000 tons when fully loaded, and yet, it is the barriers like MOSE and the Thames Barrier that stake their claim as the largest movable structures. With such astonishing size and weight, the question arises: how do these structures operate with such precision and reliability after remaining dormant for years? The answer lies in the ingenious interplay of hydrodynamics, steel engineering, and an understanding of pressure that allows these barriers to function. To decode this complexity, we must first examine the physics at play. Each gate of the MOSE system functions through a concept known as hydrostatic pressure. When these gates are submerged underwater, they experience an upward force due to the displaced water, and, this is the trick, this same force is what keeps the gates firmly sealed against the incoming tide. To visualize this, consider that when any object is submerged in water, it displaces a volume of that water. The hydrostatic force acting on the bottom of the gate increases with the depth of the water. Engineers have calculated that for every additional foot of water above a submerged object, an additional 42 pounds of force per square foot is exerted. When we apply this to the MOSE barriers, with gates as tall as 6 meters, we see that the bottom of each gate can experience thousands of tons of upward pressure. This extraordinary force locks the gate in place and prevents water infiltration, achieving a perfect seal when commanded to rise. Comparatively, the Thames Barrier, which spans over 500 meters and features 10 vast gates, operates on remarkably similar principles. Each gate is housed in a concrete chamber and is equipped to rotate upwards from its horizontal resting position when the tide rises. With each barrier weighing approximately 300 tons, the physics remains the same: the force of the displaced water seals it tighter against the onslaught of the Thames. Now, let us delve deeper into the operations of the Thames Barrier. It was inaugurated in 1984 and has been a pivotal part of London's flood defences ever since. Remarkably, the barrier is designed to operate using hydraulic systems and robust mechanical hinges that can withstand the immense pressure generated during high tide. In fact, the gates are capable of withstanding a force of over 1,000 tons during such moments. One might wonder, in a world where machines often fail under strain, how can these complex mechanisms remain dormant for years and still function flawlessly? The answer unfolds through two engineering marvels: meticulous maintenance and the careful choice of materials. Both the MOSE system and the Thames Barrier utilize corrosion-resistant steel and flood-proof hydraulic systems that are rigorously tested to ensure longevity against the demanding marine environment. Imagine a kettle boiling water. While a typical kettle may serve you tea after just a few minutes, these barriers are designed to remain dormant for years, yet be prepared to instantly lock into action. They function like a brake pad the size of a building, effortlessly preventing catastrophic flooding. Each structure is strategically placed at critical junctures, ensuring that should the moment arise, they are ready to spring into action without preconditioning. But there's more beneath the surface. Another curious aspect of these gates is their counterintuitive design when it comes to longevity and maintenance. Conventional wisdom suggests that constant operation would lead to greater reliability. However, engineers have found that allowing the barriers to remain largely inactive is beneficial. This operational choice minimizes wear and tear on moving parts and mechanical systems, ensuring that when these colossal structures are needed, they rise to the occasion, performing as if they were brand new. Now, consider this word of caution: many people assume that the effectiveness of flood barriers lies solely in their design and sheer size. However, the real intricacies revolve around their operational tactics and the strategic decisions made during their construction. Underestimating natural forces could lead to speculation that these structures are impervious to failure. The reality is, their true strength comes from meticulous planning and adaptable engineering. This teaches us a critical lesson: many assume that bigger is always better, or that more complex designs yield superior performance. In the worlds of MOSE and the Thames Barrier, we see that simplicity governs their design and optimal functionality. Instead of complex machinery that could break under pressure, the engineers opted for designs that harness the very forces of nature to achieve their goals. In the middle of this discussion, let me pose a question to you. Which of these machines would you least want to be standing next to when it's time to rise? A massive ship? An enormous crane? Or perhaps a flood barrier poised to engage its full might? As we move toward the conclusion of our investigation, it is fascinating to note that the topic of structural life and fidelity does play a key role in the longevity of these movable structures. Both the MOSE and the Thames Barrier systems are designed to perform optimally not only amidst severe weather but also during the calmest of days. Their activation systems are engineered to respond to environmental pressures, with sensors monitoring water levels, tide patterns, and even storm predictions. As storms surge and tides swell, thousands of tons of steel will rise, acting as the first line of defense against devastation. Let us reflect on the extraordinary interplay of man-made engineering and natural forces. These gates, embodied in steel and buoyed by hydrostatic principles, serve as reminders that engineering can craft resilience, even in the face of inevitable change. They represent a fascinating duality: massive and immovable when resting, yet deftly agile, instantly rising to protect centuries of culture and history when the tides threaten. Both the MOSE Barrier and the Thames Barrier have proved invaluable in protecting their respective cities from the ravages of climate change and rising sea levels. Through purposeful design and seamless execution, these flood barriers emerge as a testament to human ingenuity and determination. In closing, we are surrounded by impossible machines that somehow just work. The next time you cross a bridge, marvel at a crane, or observe the tide, take a moment to appreciate the intricate engineering that lies beneath the surface. It is a silent guardian that relies not on brute force, but on an understanding of the very nature of water itself. Subscribe, one giant decoded at a time. Let us now examine the impressive assembly of components that allow the MOSE Barrier and the Thames Barrier to seamlessly handle the forces of nature. Tucked away from plain sight, the gate mechanisms are delicately balanced systems that ensure their operational readiness, even after prolonged inactivity. At the core of these gates are sophisticated hydraulic systems, the very lifeblood of their movement. In the Thames Barrier, for instance, each of the 10 gates is controlled by hydraulic actuators. These actuators utilize pressurized fluid to rotate the gates from their resting horizontal positions to a vertical stance that shuts out the encroaching waters. The hydraulic pressure is generated through a series of pumps housed in the nearby control building. Each pump is capable of producing pressures exceeding 200 bar, ensuring that the large valves of the gates can exert the necessary force to rotate against potential tidal pressure. As we focus on the MOSE Barrier, it is worth noting how this system is designed to combat the specific challenges of the Venetian landscape. The lagoon of Venice is not only a cultural gem but also a delicate ecosystem that faces rising tides exacerbated by climate change. The intricacies of the MOSE system account for this uniqueness, showcasing an engineering marvel specifically tailored for its environment. The MOSE Barrier consists of not just the gates, but also an elaborate network of check valves and control docks spread across the lagoon. This intricate planning allows for real-time water level monitoring and automated responses to changing conditions. Engineers estimate that when activated, approximately 600 cubic meters of water are simultaneously pumped out from the barrier's subsea enclosures to facilitate quick gate deployment. The process is reminiscent of a well-rehearsed ballet, with each component functioning in harmony for the greater goal of flood prevention. A lesser-known yet fascinating aspect of the Thames Barrier lies in the design of its individual gates. Each of the gates is made of galvanized steel, enhanced for corrosion resistance, a crucial factor given the barrier's positioning in one of the busiest waterways in the United Kingdom. The steel undergoes rigorous testing before being put into use, ensuring that it can withstand the erosive environment while maintaining its structural integrity. The gates are approximately 22 meters wide, equating to the dimensions of an entire football field, and up to 7 meters tall, a physical embodiment of the magnitude of the engineering challenges faced. One particularly interesting capability of the Thames Barrier is the incorporation of flow control devices. These devices enable engineers to manipulate the flow of water around the barrier, enhancing its operational capacity during particularly challenging tidal events. Imagine trying to adjust a large dam's gates from a distance without being in perfect control of the water flowing past. This is precisely the finesse required to maintain efficacy during high-stress situations. Moreover, the timing of the operation is equally critical. The Thames Barrier has been strategically designed with environmental conditions in mind, allowing only a 4-hour window during high tides when the barrier can fully rise. This fine-tuning is paramount for effective timing and coordination. If the gates are deployed too early, they can impede the natural flow of water; too late, and the rising tide could allow catastrophic flooding. This calculation requires precise timing and advanced monitoring, which is what the engineers have painstakingly developed. Yet, while these barriers and their mechanisms may seem foolproof, history teaches us that everything comes with risks. In 1953, the North Sea flood claimed over 200 lives in the UK, sparking a re-evaluation of flood defences. The lessons learned from that tragedy spurred on resilient designs for barriers, which led to the eventual construction of the Thames Barrier itself, inaugurated in 1984. However, the MOSE barrier faced its own challenges. Activating for the first time in 2020 during a minor tidal rise, engineers faced the unknown: would the system they had meticulously designed actually hold? It was a pivotal moment, filled with anticipation. Multiple tests were conducted over weeks leading up to the event, all clearing the way for that historical first deployment. And as the gates rose to meet the tide, they performed exactly as envisioned, sealing off the lagoon with the reliability and precision expected from such revolutionary engineering. While both barriers share similarities in their fundamental principles, a telling difference presents itself in their design intents. The Thames Barrier was conceived as a proactive safeguard, designed for long-standing use and confidence against predicted flood events. In contrast, the MOSE barrier was developed with a different perspective. Venice's unique culture and layered architecture require a system not just for flood control, but one that respects the delicate balance of preserving a historical city. To further illustrate the unique characteristics of their engineering, one can explore the comprehensive safety protocols embedded within these systems. For example, the MOSE barrier is monitored via an array of sensors that track not only water levels but also structural integrity. This real-time data is transmitted to control centers, where expert engineers can make instantaneous decisions. In the case of a potential malfunction, backup systems are in place, including emergency pumps and alternative actuation systems that can be triggered for immediate manual control. Meanwhile, the reliance on automated systems does pose a critical question: how does one ensure that these mechanisms, which may sit idle for long periods, remain functional? Additive processes come into play. Mechanisms undergo systematic checks and balances at set intervals, including lubricating parts, cleaning sensors, and assessing hydraulic fluid quality. These maintenance activities are akin to the routine inspections of naval vessels, which, despite prolonged dock periods, are brought back to life to perform their duties without fail. Additionally, another intriguing comparison can be made between flood barriers and traditional ships concerning buoyancy and weight distribution. While ships rest on water and rely on buoyancy to float and maneuver, flood barriers like the Thames Barrier remain submerged until activated. Their mechanisms are thus intimately designed to engage the immense pressures exerted by the tides while maintaining stability at rest. When the gates are lowered and sealed, they act as vast, silent sentinels guarding cities, the stillness of their dormant form wrapped in the potential energy of their purpose. Each of these barriers represents an inscription on humanity's quest to thwart the unpredictable forces of nature. Engineers and architects collaborate not only in the realms of steel and hydraulics but through the lens of community preservation. By theorizing, designing, and building resilient infrastructure, they hold the futures of cities like Venice and London in their hands. This interplay between design and community engenders a profound realization: these remarkable movable structures are not only means of defense but are intricately woven into the cultural identity of the places they protect. Venice breathes through its canals, and London rises from the banks of the Thames, all while the silent guardians stand watch. Drawing together the threads we have woven throughout this exploration, it becomes evident why these massive flood barriers would triumph over traditional ships as the largest movable structures. They are engineered not just to withstand dynamic forces of nature but are designed to serve a specific need, those of preservation and protection, illustrating the sheer brilliance of human ingenuity when challenged by the naturally chaotic world. As we close this chapter, we are left to ponder the duality of these structures, vast yet unobtrusive, powerful yet understated. They remind us of the quiet engineering marvels that surround us. Innovations like the MOSE barrier and the Thames Barrier exemplify the blend of art and science, history and future, ambition and caution. We are surrounded by impossible machines that somehow just work. The next time you cross a bridge, marvel at a crane, or observe the tide, take a moment to appreciate the intricate engineering that lies beneath the surface. It is a silent guardian that relies not on brute force, but on an understanding of the very nature of water